There are a few smiles in the room. Show my hands. I'm going to guess 75%, but I could be way off. Who's seen Stranger Things? Oh, yeah, just not Mark. Mark, are you the only one who didn't see it? I haven't. Randy and Mark are two outliers. They haven't seen Stranger Things. Okay, so let's see, clicker. Here we go. Okay, so I took a lot of liberties with this. This is our displacement ventilation class. My kids love the show, and it's almost Halloween, so I'm allowed to have a little bit of fun with our content. If you see, well, since 75 or 80% of you saw Stranger Things, those of you who haven't, you get a preview, just to get us all kind of reacquainted with, because that show hasn't been on for at least a year and a half. So we're just going to reacquaint, because we are going to definitely be using some stuff from Stranger Things in this presentation about displacement. So, Sienna, please take it away.
Something is coming. Something hungry for blood. What is it? The Demogorgon!
We're in deep shit.
Now we have to go.
Later.
See you tomorrow.
Good night, ladies. Kiss your mom night for me.
Will is missing. I don't know where he is.
99 out of 100 times, kid goes missing. The kid is with a parent or a relative.
What about the other time?
What?
You said 99 out of 100. What about the other time? The one. The one.
Will! Will! Guys, I really think we should turn back.
Did you guys hear that? That's not Will. You're in trouble, aren't you?
We've sealed off this area.
This is where it came from?
Yes.
And the girl?
She can't have gone far.
Find her.
Do you really think it was a coincidence that we found her at the same place where Will disappeared?
Something is going on here.
What the hell?
She knows about Will.
Is there any way that you could reach him?
Yes.
What if this whole time I've been looking for Will? I've been chasing after something else.
Okay, so this is there's a few looks here of the upside down. And so what I'm pushing to create here is just a little bit of a different world than the one that we're used to living in. Michael Jackson kind of nailed this upside down thing from Thriller, if you're old enough to remember that. And if you haven't, you should definitely go back and check this out. Another look of the upside down. Isn't this displacement upside down? Isn't it kind of the opposite of what we're used to? It seems to be counterintuitive, but diffusers to the floor, but it's exactly what we're dealing with. So just, oh yeah, I gotta do that. So showers and baths, if you get my blog, you probably saw this, this might be a couple years ago, but I've been talking about the upside down shower for like 10 years. I put it together in a blog post, and we did this cute little video. You'll have to click on it. From a couple of years ago, just displacement ventilation.
Factors like
short order.
drinks, body type, and clothing all affect our personal comfort. At the same room, men and women naturally feel comfortable at different temperatures. What feels warm to him feels cool to her. Factors like food, drinks, body type, and clothing all affect our personal comfort. At the same room temperature, some will end up being hot, while others shiver. In the ideal world, everyone would wear spacesuits that allowed them to control their temperature and humidity to their own personal comfort level without having to affect the person next to them. Sadly, office astronauts have other problems. For one, it's really hard to type with those big gloves on. Displacement ventilation offers a solution to these problems by using the heat generated by people, computers, and the like to take fresh, cool air from vents low in the room to displace stale, warm air, rising to a return vent in the ceiling. Also, some of these vents can be turned on or off individually, allowing for more personalized comfort. In other words, displacement ventilation is like an upside-down shower with the drain in the ceiling, always showering you with fresh air of your choosing. While traditional mixed ventilation is a bath where you live in a slowly more disgusting environment as the day goes on. With displacement ventilation, everyone will have their dream comfortable environment, even if you're still at the office.
So displacement ventilation in 2 minutes, yeah. Back to our slideshow here. This is maybe a little more, you'll have to play this one too. A little bit more of what we're used to thinking of, seeing when we talk about displacement ventilation. Videos available with price.
This smoke test demonstrates the thermal plume, which is the effect of heat sources warming the surrounding air and causing it to rise.
Yeah, and I cut that short because we're going to be using it a little bit more later. So what I'm hoping today is that you guys get a couple of important takeaways. Number one, we're playing around with this upside down world where we have a different set of rules, where we operate a little bit differently. We're going to talk about the rules that we live by right now, maybe how that can change. And also, every time that you see a Stranger Things ad, you're going to either be thinking of displacement ventilation, airflow, or price industries. So if I get that done, I'm going to be pretty psyched. So here we go. Here's our agenda. You can see I'm taking a lot of liberty. There are 5 things that are real HVAC principle type things. There are a couple things that I'm having fun with the theme. So we're just going to mess around a little bit. In the background, Chris Burrows from Price Industries. He's the director of sustainable. He's going to be presenting in the middle of this. I don't think can you see him? Yeah, he's up there. Here you can't, but you'll be hearing him soon enough. And then we also have 3 great guest speakers. So Mike, Kirk, and Stacy, who are going to be kicking off the second half of this. They are displacement, I would call them now displacement experts. So probably a lot of the reason that you're here is because they're here. You may have heard me chime in about displacement a handful of times in the past. Hearing it from them is way more valuable than hearing it from me. Okay, moving on. Using that little Christmas light thing. First principles. I get a little bit frustrated when we talk about displacement ventilation is then, okay, here's displacement ventilation. You put in the air low, you exhaust it out high, it finds heat sources, and that's the way it works. That is fine. And sometimes displacement kind of gets pigeonholed into the wrong spot. So let's go all the way back to what is it for? Like if you, from a marketing perspective, like Mike and I work on our marketing, whenever you make a marketing message, you go, who's it for? Who's it for? So HVAC, who's it for? Let's talk about this. Here's our real world slide. What drives our decision-making? Money, time, production. Money, time, production. If you boil down all your decisions over the course of a day in what we do, money, time, production. So what are the drivers of system? We are the ones who drive system selection, are we not? What drives it? Compliance, often the minimum, right? We have to do the bare minimum, often that's where our constraint is. The customer, does the customer really care about the HVAC or is it just like, how can I get something in that meets code, right? Some architects and owners are more interested, often there's limited interest. How comfortable is the designer with the system? If you just do rooftop units, then rooftop, that's the hammer and the nail thing. Everything looks like a nail. Before I go into that, people don't. I mean, do you really want to do something different? Maybe you do, maybe you don't. But often it's like, I found a reason not to do something different. Yes, I knew it. I knew I could find a reason not to do this, and now I found it excellent. We're going back to VAVs or rooftops or boiler chiller or whatever it turns out to be. Timeline, I don't have time to do something different. I can't afford to do it. I'm constrained. Repeatability. Oh, I have 4 people that work for me. I have 30 people that work for me. If I do something that we've done before, I can delegate this task to somebody else and still be effective. Predictability. I don't want any problems. I don't want to be called back. I don't want to go out to the job site. I don't want a call that I'm not prepared for. I don't want to do that. So I'll do what I did before. That'll get me the results that I want. First cost, always a constraint. You can design the Taj Mahal. If your first cost doesn't line up, well, then here come the scissors and the knives and the chopping. And finally, well, we all gotta make a buck, right? We can't just afford to do willy-nilly things. So ultimately, I gotta anticipate a profitability in the project. If I do what I did before, it's a better predictor of making a profit on a job. That's true for a contractor, that's true for an engineer, that's true for a GC, that's true for an architect. It's across the board. What did I not cover in any of those things? Comfort. Document. Right. So she looks not comfortable. What's it all for? It's supposed to be for the people that work there. We have maybe lost our way a little bit. So we're gonna push back towards the occupant. Now, here's a rhetorical question. If you had double the time and double the budget on your project, what would you do? Rick, what would you do?
Yeah, I guess I would take a little time to think about the system concepts. Is there something different that we could do?
Right? If you had this, my bet is you'd improve the efficiency. You'd go from air-cooled to water-cooled. You'd go from water-cooled to geothermal. You'd go from rooftops to air handlers. But would you go to comfort? Probably not. I don't see this happening much. I've been pitching displacement ventilation for 20 years. And this is what I see when there's flex in the budget doesn't address comfort. It certainly doesn't address air quality either. So we're all swimming in the same pond, pun intended, I guess. But this is what we do, and maybe it's not the first thing we should do. So here's our upside down. The other world that we're creating. What's number one? We're gonna say in this new world of the upside down, comfort is king and queen. Safety is up there. Energy, you know what? When we do displacement ventilation talks, we talk about energy being a driver. Let's forget it. I mean, it's there. If you do a displacement project well, you will save the client energy. But what I end up finding often when you get in the energy side is a bunch of yeah buts. What about this and what about that? Let's make the point that if comfort and safety are the most important things in this world, and energy is kind of down the line, or maybe it's going to be better or the same or close, let's not worry about it. We're going to talk about energy and airflows and all that kind of stuff. What I really also like a lot about displacement ventilation is that there's a lot of simplicity in it. We're going to be talking about that. And the last thing is pride. When I say pride, I know that the 3 examples of engineers up here who have done these are really proud of the work that they've done when they've done something different. Now, you all, if Randy, you can fall out of bed and do a VRF system or a VAV system. It's not a giant challenge for you. You've been doing this for a long time, right? When you do something different is where you get that feeling of, oh man, client's really happy, general contractor's really happy, it went in the way it was supposed to go, I feel good about it, and the client's thrilled. So that doesn't happen all the time. I'm just catching up here, guys. My notes that I'm not really using. Okay, so we're gonna have a pop quiz. And Sienna, you'll have to show the question. So I want, will you show the question, please? Just in that little, oh, you gotta be careful where you click it because sometimes it, yeah, there we go. The most important aspects of occupant satisfaction. I probably could have phrased that question better because you could say, well, I wish I had made more money at work. That's not exactly what we're talking about. We're talking about generally about comfort. There are not 8 answers on the board. There are 4. I would like to see 2 from our studio audience and 2 from our remote audience. Who here has a thought about occupant satisfaction? Dave, temperature. Temperature, number 1 answer on the board, correct? Very good. Any other? Air quality? No. Oh. The X is down here. You can do the X thing. It's loud. Oh, I'll just pretend it happened. Do we get anything from our remote? Anybody chime in on the? Oh, come on, remote people. Stop doing the job that you're pretending, you're pretending to watch this and then you're actually doing your regular job. Oh, wait, here we go.
Humidity?
Humidity, the number 2 answer on the board. Done. Next.
Draft.
Oh, I'm sorry. Humidity was 3. I gave away 2. Sorry about that. Draft is in the chat. Who was that?
Ben Patterson.
Ben Patterson. Okay, and number 4.
Noise.
No. Not noise. Although, yes, it's true. Anything in the chat? Oh, wow, the group got stumped. Well, you were all gonna get a trip to Tahiti if you got all the answers right, but oh man, too bad. Oh, they got it right. I lied. Number 4, radiant temperature from surrounding surfaces. Somebody looked that up though. All right, nice job. We have 1 more quiz. Okay, Sienna, please show the question. What affects your metabolic output?
Your age.
I'm gonna give that one. That's number 3.
Activity.
If we have activity level.
Activity is number 1.
Diet.
Number 2. Wait, are we gonna get to 8? I don't know.
Gender?
No, sorry, gender, yes, but that's not one of the 8 answers. Guys, got 5 to go. How about a hint?
Medications?
Didn't have that on there. When's the day when you feel inordinately hot at work? If you.
Illness.
Yep, number 8.
Temperature?
So hey Tom, Amy online said clothing. Is that one of them?
Wearing? That would be, I didn't have that either. It's not exhaustive. There's only room for 8. What am I supposed to do? If you drink too much, if you don't drink enough or you drink too much coffee, number 7, caffeine, water intake. Anybody have a really bad day and find that it affects them physically? Number 6.
Turnover.
if you're a guy and you're married to someone who's between 40 and you're married to a woman and they're between like 40 something and 50 something, metabolic changes, which is number 4, hormonal metabolic. Yep. And then number 5 is how much sleep you got. Okay, great job, everybody. Sort of. Pretty good. Pretty good.
Here we come.
Okay, I'm taking some liberty. This is the section where I take some liberties. I'm just gonna advance here, sorry. I'm a Stephen King fan. If anybody's seen or read the book Carrie, the book is about telekinesis. If you saw it, this is the old John Travolta and Sissy Spacek and somebody else, and she's throwing things around the gymnasium with her mind. And in the book, he has all these studies that he quotes for like true university grade level telekinesis studies. And I'm like, oh man, this stuff is for real. So I did an AI chat. There's none. He did it. He totally snowed me. I thought I was going to find something. So the closest thing I could find in the real world, this guy, Dr. Bruce Lipton, he's PhD. He did teach medicine at UW School of Medicine. And the idea that he presents, he's kind of on the speaker circuit. He talks about how your mind can turn on and turn off. It can change your cellular behavior. So we all have the potential to develop cancer in our bodies. Some people do, some people don't. He postulates that what we think about and how we feel creates the environment for the cells don't really know what's going on, but your mind and your thoughts and your emotions drive cellular behavior. So that mind-body connection and all that woo-woo kind of stuff, he's like, that's real, and he speaks on it. So that's as close as I could get to telekinesis in the real world, mind controlling physical things. Yeah, all right. This is a fun video from Stranger Things on telekinesis.
Incredible.
All right, so a section maybe you wouldn't have thought we'd cover today is thermostats. Smart thermostat. How smart is it really? If this baby were smart, it would know what I ate for breakfast. It would know how well I slept last night. It would know if I worked out. It doesn't. I mean, can it do some cool things? Yeah, it kind of can. You know, you can tell it what to do from remote. You can turn it down or you can turn it up. But how smart is it really? I don't think it's that smart. Not particularly. Here's a video that Price put together for me last Friday. This is overhead mixing. This is how it's supposed to work. If you've never seen a smoke video like this before, this is how it works. We're gonna stir up the whole room, like our big bathtub. Everything's the same from the top to the bottom, left to the right. Doing a perfect job. It's getting all the way to the floor. Notice it's 55 degrees. It's 20 degrees colder than the space. The air change rate is 4. It's an 8-inch diffuser. When we do 200 CFM, it's an 8-inch diffuser generally, right? Does that sound, I'm seeing him nodding over here. Okay, great. And, oh, quick pop quiz. If you look in the book and you get your throw data, what temperature is the air? And who knows the term for it? And if you're from airflow, you don't get to weigh in on this one. See Randy's lips moving.
It's a standard temperature, but I don't know what it is.
It's called isothermal, and the temperature of the air coming out of the diffuser is the same as the temperature in the room. So whenever you do a calculation for throw, you're supposed to take into consideration whether the air is cooler or hotter. Hotter throws further, cooler throws shorter, but then you've got drops, so there's all these different calculations that need to happen. Anyways, that's isothermal, and that's how catalog data is. Fun fact, we have thermostats at Airflow. They work just like every other thermostat. Yet, if you walk around this is not all of the space heaters that I found. But this is many of the space heaters that I found. So we have these thermostats and our office is super comfortable, right? No, why is that? Apparently these thermostats are not as effective as I think that they should be, because I would ban electric space heaters because they're really expensive to run. Bad COP, all that kind of stuff. So we're in the business. I'm putting up with space heaters. This is a comfort issue. Why is that when we have thermostats? Good question. Here's another video. Let's take that same diffuser. What do we do in a VAV system? Well, we're gonna cut the airflow down and we're gonna elevate the temperature. Oh man, this is working great, isn't it? What are we accomplishing?
Not a whole lot.
We have very comfortable ceiling tiles. We've shortened the path to the return because we're not doing any mixing. Is this good? This is our gold standard. This is, I'm gonna put in a VAV system, it's energy efficient, it does this, it does that. Now, this is, what's supply temperature is 85 degrees. What's the highest supply temperature that you guys are using these days? Is it 85? What, 95?
95.
100? And do I hear 100? Anybody using 100?
Every once in a while.
Every once in a while. Oh, okay. Now, we're doing 2 air changes instead of 4. Minimum ventilation VAV reheat system is it half? Oh, 30%, right? I mean, when you do a VAV box automatic calculations, the airflow. So let's cut this airflow instead of half to a third, and let's raise the temperature to 100. Is this getting better or worse? It's getting way worse. But let's keep doing this because it totally doesn't work. But this is what we do this every day. We've been in buildings that we do this all the time. And yes, some exterior zones have perimeter heat. And sometimes we reopen the box. But usually we reopen the box to 50%. We don't reopen the box all the way to 100%. Sometimes we do, but this is neglected in all the calculations that we're making for VAV systems. So again, this is kind of that first principles thing. Who is it for? Well, it's not really for anybody here. Okay, back to Stranger Things. here's some of our cast of characters. They're all typical 80s kids. They all look the same. They're all about the same size, right? But when we go into our real offices, they're not all same size, right? Everybody's a little bit different. We're only allowed to make fun of white men these days, so I'm gonna make fun of white men. The sales manager is kind of a big guy. And what's the point here? The point here is at 72 degrees, who's really happy? Well, the big guy here, the sales manager, what's he running? And the red is kind of giving us a hint that he might be running a little bit hot. Now, you can say that nanas don't usually work in businesses, but my 84-year-old mother works here. Never gave her a job, someone else did, and she's been working here for 20 years. She works a couple days a week. She periodically does complain that it's a little bit cold in her office. Michael B. Jordan, now if he's looking like that, he's on a cut. If he's on a cut, that means he's eating fewer calories than he burns. If you're on a cut, you're running cold. Jennifer Garner is about my age. And when I say hot mom, she probably is running just a little bit hotter than when she was 30 for various reasons. And then hangover Hank is just feeling it, right? It's just feeling it. Okay. Now, here's the upside down. In the upside down, everybody's happy at 62 degrees. No way, Tom, that's cold BS. How can they all be satisfied at a supply temperature of 62? Doesn't make any sense. Okay, let's take a look at a video.
This scenario demonstrates what happens to the supply air as it encounters heat sources with different loads. Each heat source will receive supply air that corresponds to their heat output. Higher heat sources receive more supply air, while lower.
You see what's going on? We're matching the load. So when we talk about, oh, displacement seeks out heat sources and it does this thing where it comes out of the wall slow, that's not what's really happening. What's happening is there's a pool of available cooling. We're running hotter than the supply air, which is anywhere from, we've done 52 degrees, right, Kirk?
Yeah.
All the way, 62 is typical, 67 works. But what we're doing is load matching. And the driver is you. You are the driver of the HVAC system. Lower load, lower cooling. Higher load, higher cooling. So sales manager, you know, folks, I'm always running hot. I'm always running hot. They're not hot because they're pulling the cool air to them. And someone who's running cold doesn't pull any air or very little at all. That's the magic of this system that often gets overlooked. Everybody is comfortable. Please continue.
Heat sources receive less supply air, thereby maintaining excellent occupant comfort.
We can watch that again and again and again. It's so cool. It's so cool how it works.
This scenario.
This is, Price ran this one for me. We got a 40 and an 80 and a 120 watt mannequin. This one's a little harder to see. The 1/3 full is a little bit easier. See if you can figure out which is which. I know I'm a dork, but I could sit here and watch displacement videos. That first one's got to be 40. Chris, is the first one 40?
Yes, I think that's what we established. Yeah.
We have 40, 80, 120. Okay, this is so cool. All right, we're gonna go to the next one. One more. Oh, that's Ryan, who's in the background setting these up. I think it makes its point, right? 40, 80, 120.
Mm-hmm.
You think if we move the diffuser around, it would change much? No. Probably not. We'll talk about that later. Okay. So this is a blog post. Got Snoop with his solid gold thermostat. This is pretty close to how it works, don't you think? I mean, in a displacement system, you're controlling the supply air temperature. There really is no need for a thermostat in the space. If, assuming, yes, you could create a scenario where there's no load and then you fill up the room with displacement air, but this is how it works. We all have our own thermostat and it works just that way. Really cool. Okay. Section 4, air quality. Everybody. Do we know the answer to this? The solution of the problem of pollution is pollution, right? Is it? So Sunday, kids are still asleep maybe, having a cup of coffee, the sun is coming through the window. It's that rare day that you can see all the floating particles around. And if you go, oh, I'm gonna put more outside air in here, do the particles all disappear? They really don't. You're just mixing them faster, right? So I'm gonna turn this, well, let's see, Chris, we gotta figure out how about I do this and then I'm gonna turn the study over to you. Does that sound okay?
Yeah, sounds good.
Okay. If you've seen me present displacement before, sadly, I'm gonna reshare some old data because it's really old. Some of it's almost 20 years old. So when I first became familiar with displacement ventilation, I was taking Neil and Glenn Greshel, the Greshel company, out for dinner. And we went to Potawatomi. And I had just gone to Price and seen their smoke lab, like you just saw their smoke lab. And that place, man, it was just so filled with smoke. I smelled bad, everybody smelled bad. Nothing against smokers, it was just, there was so much smoke, it was incredible. So Potawatomi had done, well, it'll be easier to see when I zoom in. Okay, so Potawatomi, first of all, 4 air changes per hour. This is 100% outside air. That's a lot of air, right? A lot of 100% outside air with energy recovery units. So they're definitely committed to cleaning up the air. So they add this dynamic air cleaning, which is kind of, charge the particle. It's more efficient than just mechanically grabbing a particle. And notice, so we're looking at particulate size, 0.5 microns, 0.7 microns, 1 micron, 5 microns. Why did they do the study at 0.5 microns? Tobacco particle. Any other things that are right around 0.5 microns? Germs. Virus. Virus is 0.3 to 0.5. So they put in this dynamic air cleaning and notice they made a huge impact. Like look at RTU1 at 1 micron, 6-fold reduction. RTU2, 5-fold reduction, 70% reduction in RTU3, really good at 1 micron. You go to 0.5 micron, they didn't do very well. But if you look, when we added what do? We took out round diffusers and we put in displacement diffusers and dropped the air to the floor. And look at the reduction, it's 5 to 1 in some spots. Now there was other things going on, so that's why the data is not consistent across the board. So how exactly they tested? I think they just had a particle meter, they brought it back out and tested after they changed the diffusers out, But big difference, right? Well, for them it's cleaner. It's cleaner in the space. Now in our, post-pandemic, that particle counting can be a big deal. Now, are we eliminating 0.5 micron particle? No. But there's definitely a correlation to how much there is in the space in your likelihood of getting infected. Okay, so Price goes ahead and they go next level study, and Chris is going to take this on. He and Ryan Johnson are the authors of this article. If you get Price's blog, this is in there. But Chris is going to talk about this study and the impacts, and it was definitely revolved around COVID and aerosols. So Chris, take it away.
All right, sounds good. Yeah, thank you, Tom and the Airflow team for getting us plugged in here and offering us some time to talk about this study that we were a part of. So back in 2020, Price Industries, we as a company, we embarked on this adventure to look into the different air distribution strategies and how they have an impact on airborne particles of different sizes. You can see they're listed as part of the abstract of this article that Ryan and I put together. 0.3 microns to 5 microns as the different sizes of particles that we measured, because we wanted to understand. Now, granted, Tom and the team at the previous project mentioned they had done this decades before, but as far as understanding this in an office space is something that we wanted to investigate. So we did this study in conjunction with Purdue University and some of the aerosol scientists there. And we actually reconfigured our space, one of our spaces in our labs, with this setup here that's shown on the screen. So we've got MV standing for mixing ventilation and DV for displacement ventilation. We looked at 3 different air change rates, 2, 4, and 6. And between mixing and displacement, we kept the airflow CFM per square foot the same, as well as the different thermal loads. We did change the thermal load based on the air change rates. And then the mixing ventilation supply was anywhere from 53 to 61 degrees. And then you can see in the bottom right there, the temperatures we reset to for the displacement air change rates, 57 up to 67. In terms of the instrumentation, so we had a particle, it's a BLAM nebulizer. Always have fun saying that. So BLAM is the acronym for the particular device there you see. And it was atomizing a saline concentration. And then at each of the occupants, we had 4 occupants set up, thermal mannequins with the trees there shown on the left side there, that were measuring the particle counts. And there was multiple sensors throughout the elevation of the space, so we can understand particles as you move upwards from the floor to the ceiling. And then we had obviously just the generator at one specific occupant location. Okay, so the impact, and I'm just assuming that nobody's read the article. Hopefully there's a massive portion of people that have already read it, but again, this was back in.
I read it, Chris. I did. I swear.
Hey, thank you, Tom, and maybe one other. I think I heard there. So yeah, back in 2022 in December, that's when this was published. This was the impact of the study. So just focusing on that, the left side here first. Obviously showing the 3 air changes, 2, 4, and 6, and you can see just in general between MV and DV. There's a substantial reduction in particle count. So number of particles per cubic centimeter is on the y-axis there. And then what we've got represented from the different colors of bars is the different occupants. So occupant A, which is not shown here, that is patient 0, if you will, with the nebulizer. And then B, C, and D sat either adjacent or across from occupant A, where the simulated sick patient was, sick person. So you can see that quite interestingly, occupant C was the occupant furthest away, but still in the general workstation area to occupant A. But occupant C, across all the different air changes, had shown a lower particle concentration than B and D. So this was a work setup where there was just 4 desks. It had those plexiglass dividers in between each of the spaces, which was pretty common during 2020 and 21. And occupancy was the furthest away. So if you envision, you go back to Tom's smoke videos, the discussion that he had is if you move the thermal plumes around, the occupant loads, basically the further you get away from an occupant that is giving off some sort of particle contaminant, those plumes are going to more effectively bring a lot of those up out of the space to be exhausted and returned or returned back through a filter. So this was done in close quarters, but yeah, you can see pretty consistent results between the different air changes, which VAV is a very common approach in the US with displacement ventilation. All right, so next slide, we're going to zoom into the graph on the right. So this is looking at E sub Z, and I'm thinking most people in the room are familiar with that term. It's zone air distribution effectiveness. It's quite a mouthful. Represented by E sub Z. This is out of ASHRAE 62.1 and really just throughout ASHRAE documentation in general. And that is, to simply put it, at risk of oversimplifying it, but really just a ratio of the contaminants measured in the breathing zone under the amount of contaminants measured in the return unoccupied zone. So the higher that value gets, the better the air quality is in terms of particle measurement. Because example, at 2.0, you've got twice the amount of contaminants above the occupied space. So with that, the E sub Z, you can see that we measured the E sub Z away from the occupants where there's less air movement, going back to that smoke video. And you can see displacement in the blue bars, kind of mixed results, but hovering around that 1.1 on average between the different air changes. But when you go to the breathing zone, you have a significant increase in air change, or rather zone air distribution effectiveness. And that is because you go think back to that smoke video that's helpful in demonstrating this. You essentially have all that air change happening where we want it most. And ASHRAE publishes 1.2 ventilation effectiveness as kind of the baseline, and that was really as a result of the worst case that they had seen in the research. And that's more of an average E sub Z taken throughout the space. But again, that middle portion of E sub Z is showing the breathing zone and the measurements taking where the occupants are, or the thermal mannequins in this case. So it's pretty substantial. And with this system, we're really moving the air as quickly and effectively as we can to where the occupants are in these spaces. Now, the last thing there on the right showing air change effectiveness, not to get too into the technical acronyms. This is one that, as I've talked to many groups about these terms, air change effectiveness is less understood. And it's a different method of measuring and telling us a little bit something different about what's happening in the space. It's a measure of the time constants, the time it takes for the fresh air to get from the diffuser to the breathing zone, compared to the time it takes for the air to get from the supply to the return. So really it's a little different because that air and tracer gas is coming through the diffuser itself. And we're measuring how quick it gets to the occupant or breathing zone. So that's kind of in terms of the air changes, how effective it is. And so you can see here, it's kind of around just above 1.5 up to 1.8 in some cases for displacement. And as we would expect, around 1 for unity in a mixed ventilation case.
Was the mixed ventilation isothermal test?
No, that had a delta T to it.
Okay.
So it was around 20 to 18 degrees, I think, delta T.
Cooling.
In cooling, yeah. Yeah,
So
that's a good point. These are cooling only scenarios.
Right. So in heating might be, well, you can't do heating with displacement, so it would be different. There's like white and eggshell colors. I assume that in the middle graph, the white on the left is displacement ventilation and the one in the middle is mixing at 2 air changes.
Yeah, I don't know how clear they're coming through. The white, somewhat blue on the very left of each of those scenarios is the 2 air change displacement. And then that one that's kind of fourth from the left, the light green is mixing ventilation at 2 air changes.
Got it. All right. Good. All right, Chris, we're gonna move on.
Sounds good.
Thank you for presenting this. And And usually ventilation effectiveness is measured, comparing the return to space. This is measuring the breathing zone, which is a lot different than comparing the return. Because nobody's living in the return, right? Who cares? We want all the particulates in the return so we can filter it out. All right. So this is my section on monsters. It's short. These are the real life ones. Gross. Some of them. Goblin shark, vampire bats, like that's disturbing. This is called a pangolin over here. The upper right is a tarantula hawk wasp. Upper left is the zombie ant fungus. I think the one that unnerves me the most is that Goliath beetle. And then, of course, everybody's favorite, the naked mole rat and the anglerfish. And then there's a cute, these are some of the monsters that you'll find in, they start off as the dart and they can go all the way up to the Demogorgon. A couple of the villains of the show. And then we've got a little video here about all the different evil, nefarious characters from Stranger Things. This is only a minute. I never knew all the names.
I wish they would have teased out the next monster. That would have been fun.
Right, that's true. All right, section 6, diffuser placement. This is not the fictional, this is the real. I'm just gonna touch. Where are we going? Thank you. You guys probably at some point or another have witnessed the Price training class where they talk about the occupied zone, that it's from 0 to 6 feet, 1 foot off the walls, 3 foot off the back wall is. Exterior, thank you. We have these terminal velocities. So off of a diffuser, there's 150 feet per minute. And in some ways, like who cares about 100 and 150? All we're worried about is in the occupied zone, we want the airflow to be at 50 feet a minute, right? Why is it 50 feet a minute? Oh, why is it 50 feet a minute? Pat, do you have an answer?
Oh, you don't feel the draft.
You don't feel the draft. Excellent. Excellent. Thank you. Okay. And then, so when you're looking at your performance charts, you see 2, 2, and 5 for that first 8-inch diffuser. So the terminal velocity here is at 150 feet a minute is 2 feet away, 100 feet a minute is still 2 feet away, and then 5 feet away. So if you have a diffuser in the middle of a ceiling that's 5 feet to the wall, it didn't get in the occupied zone. So that's obviously not the greatest diffuser application ever. Okay, moving on. And this is just kind of for context. This is how it gets tested. So they got a profile, they're measuring the velocity of the air off of the wall or off the ceiling. It's a lot of kind of nitpicky work. Chris, do you usually do this with smoke?
Yeah, we do throw checks with smoke and then sensor trees everywhere.
Okay.
Place through.
All right. Super fun.
Oh yeah.
Oh, there was stuff in there. And then of course, when you throw from a sidewall, the air spreads out, there's calculations for spread. really exciting again. The Coanda effect, when you're throwing a diffuser, or throwing air out of a diffuser in a ceiling, the air tends to hug, makes the throw more effective, further, that kind of stuff. When we saw those smoke videos, that's a Coanda effect. Now, why am I showing you? Technically, you are all supposed to be figuring this stuff out when you pick diffusers. Do you do that? I wonder. I wonder. Do you take into account all these correction factors? So here's our ceiling diffuser in that example. Application where temperature differentials have the greatest effect, vertical download discharge and heating as high as 40 degrees, reduce up to 40% compared to the catalog. What's the catalog data? What's the term called? Isothermal. Very good. Isothermal. And then, of course, we should be all taking into account sound. So, okay, my second diffuser, NC is 24. Oh wait, who has a room with one diffuser in it? Unless it's a 10 by 10 office, it probably has more than one. So, of course, you need to figure out the correction factors in NC if you have multiple diffusers, right? So 6 air outlets at 8 dB to your selection. Who's done that calculation before? Nobody. Nobody has. Rice uses it when they say, hey, your diffusers are loud, and then they say, oh, you should have figured this out. All right, anyways, yes, you're probably not looking at, maybe you're looking at throw data if you have an atrium that you have to throw air across, maybe. You may take a couple minutes to figure out diffuser placement in an awkward shaped room. You're probably not getting paid to do that, so you're probably not doing it, and this is, you know, for our gold standard ventilation overhead mixing stuff, this is super dull, right? Who wants to do this? Is not fun. This kid can figure out displacement ventilation. He's got to fill up his kiddie pool with water. Does it really matter where he holds the hose?
As long as it's in the pool.
As long as the water's in the pool, doesn't matter. Now, yes, Price will be like, careful with, you know, gotta be careful. You don't want this. Theoretically, this air can go 100 feet. Practically, it probably doesn't go 100 feet, but if you have a gymnasium and you have one diffuser, yeah, you might be inviting a challenge, right? On the other hand, the whole like, I gotta place all these, you just gotta get the air in the room. Because if the diffuser's here and I'm standing here, what's gonna happen? I'm gonna pull it. It's gonna come to me. It's gonna follow me around. It just does. That's how it works. I'm the signature in the room. I'm making the difference. I move the air to me. That's how it works. So if I have to pick displacement diffusers, here's the very difficult math. How much airflow do I need? I divide by 40. What's 40? Our good rule of thumb. You can make the air go slower if you want to, but it doesn't matter. If you go over 40, you create a little bit of throw. We don't want to do that. We want to be displacement purists. We want this exactly to work on buoyancy and buoyancy alone. There's no throw, there's no spread, there's no drop, there's no draft, there's no sound. We don't worry about air running into each other. We don't worry about the Coanda effect. We don't have any problems. Here's a couple of just pictures of, you can hide them, right? That's airport gate, right? Classroom. So what I like to do with architects is, well, what I like to do with engineers is, what do we do? I call the architect. You say, hey, Miss Architect, I need 14 or 40 feet of diffuser face in the wall. Are you creative enough to come up with this solution? They're like, oh yeah, wall space, no problem. We put the diffusers in the wall, we're done. You can put them anywhere. You can put them up top, drop the air in. You can have it high, you can have it low. We're gonna see examples of those when Ring and Do gets up here. Just sort of gentle reminder, 2 reminders. 1 reminder is that we do CFD. So if you're scared to death that you're gonna break the system, we can prove that it's gonna work. Number 2 is, you notice that's red at the top. Where do we wanna put our returns? At the top. We don't want to pull cool air out of the space. We want to move the air through the system. Returns at the top, they're always pulling heat out of the space, no matter what the mode is. So here's your gymnasium. Oh, wait a minute, Tom, I can't put baseboard in a gymnasium. Why am I making that statement? Well, we can't heat with this displacement, right? It's a cooling only system. Upper pictures, you can do sort of isothermal. You can do a little bit of heating, but the second you start raising that temperature, your air goes right to the ceiling. So what Ring and Do has done in a few cases is where we have a high ceiling, we don't have perimeter baseboard, what do? We heat through the displacement diffuser, and then we use destratification fans. We mix until, when do we stop mixing? All the kids get there. And all the little heat sources arrive, or the analogy, you put the cows in the barn, and all of a sudden the barn's warm again. So cooling, isothermal, heating. Heating is only for morning warm up or unoccupied modes. And we don't want to mixing and displacement. That's a no-no. We don't want to do that. Section 7, load calculations. All right, we're doing well on time here. We could spend a lot of time here. We could. I'm threatening you a little bit, but we're not. So well, first of all, let's face some cold hard facts. If we use displacement ventilation, after seeing Chris's study, can we reduce the amount of outside air that we use in the state of Wisconsin? It's still 7.5 CFM per person, right? Does that suck? It kind of sucks. You get to dance, if you're doing display, you get to dance around with this equation. Does this look like fun? It's not. It's real simple though, not at all. The flow of displacement with a reduction in load of people, reduction in load from the lights, reduction in load from external sources. Of course, we're going to take into account the air density, the specific heat of air, and then of course, the obvious temperature differential between my foot and my head. Oh man, that sounds awful, right? And if for the faint of heart, like this is what happens, like forget it, I don't want to do this. Let's go back. You don't have to deal with this with a calculator, right? We have programs to help you. So instead of being like, that sounds hard, look, just send it to us. Price has a program. It's way better to kind of work through this problem with someone who's done it before. We've done a lot of these already. So this is ugly. Don't want to deal with it, but it's easily solvable. It doesn't take a lot of time. You do your loads. You do your load sum calculate, all that kind of stuff. Send it to us. We'll play around with it. There's ways to import it if it's train trace. Chris, do you have any more import tools, or is it just train trace?
Yeah, just train trace currently.
Okay, so if you use train trace, you're in luck. If not, we're gonna be doing a little math for you. No big deal. So yes, you can pack it in on DV if you want to. Or don't quit. Stick around, play the game. Now, we're going through gates. There's gates in Stranger Things, there's gates here. What's gate number 1? Gate number 1 is gonna be like, what are we doing this for? I haven't seen this before. I don't care what, the ladies' ankles are gonna be cold if they're wearing high heels. Oh, okay, fine. All right, fine. We'll indulge you, Mr. Miss Engineer, we're gonna indulge you. And then the second that job goes $1 over budget, here comes the chops, right? They're gonna take it out. You gotta stand tall and hold it, because there's a lot of good reasons to have displacement ventilation, but know that this is gonna happen. Know it. Now, after you do it a couple times, or really once, and you're supremely confident in your ability to deliver a displacement project, they go, okay, I believe you. But first time, yeah, you're gonna be questioned and you'll have to be resourceful. There's a tool. This tool will take your calculations. You can figure out the CFM for a given space. We do it one space at a time. There's Egos and Stranger Things, and this is the reduction. So this is the load. When we do a mixing system, does it matter if it's chilled beams, fan coils, heat pumps, VAV, constant volume, rooftop units. We do load calcs the same exact way for all those systems. We don't do it the same way with displacement. A lot of the load moves out of the space. Our delta T is generally lower, not necessarily, but generally lower. How does it shake out? We'll do this performance calculation for you. This was a lobby with the taller ceiling. The reduction in airflow is 14%. The ventilation effectiveness, not Chris's ventilation effectiveness, but the ventilation, the traditional VE calculation is higher. So yes, is there energy savings in this? Sure. In every room, no. Don't hang your head on energy savings. Hang your head on comfort and air quality. And that, ladies and gentlemen, is the end of my portion of the presentation. So we're gonna take 8-minute break. We'll be back here at 11:15. I'm gonna play one short video. We're gonna turn it over to Ring and Do. We should have time for questions after. So we'll see you all at 11:15.
Let me tell you about the day I first met my friend, Derek Sivers. Derek has a blog, I have a blog. On the very same day, we both posted the very same video with an analysis of what we were seeing. Derek's analysis was more on point than mine. We met at TED a few months later and he shyly showed me what his TED Talk was about. And I said, that's fantastic. And then I was lucky enough to publish his first book. Here's the video. It's been seen 24 million times. I sped it up. It's a little janky. Sorry about that. This is the Sasquatch Dance Festival, Rock Festival. And what you see is one guy, one lonely guy, dancing to a voice in his own head. And the second guy shows up. And the second guy and the first guy are having a great time. But that would be the end of it. Except guy number 3. Guy number 3 braves the culture in front of him. He braves the idea of being seen as a outlier of some sort, and he shows up too. As soon as guy 3 is there, it now becomes safe for 4, 5, 6, 7, 8, 9, until there are too many people dancing to count. That what happened is the gravitational force, the social acceptance of this event shifted. It didn't shift when the first person stood up and started dancing their lonely dance. It shifted when guy number 3 was brave enough to show up and participate. So this can feel like a human artifact, but I want to show you some footage that I just found from National Geographic that helps us explore how deeply this goes, how time connects with systems, and that is at the heart of strategy. Here are emperor penguins. Emperor penguins in the Antarctic, once they're old enough to swim, jump into the water, maybe 2 feet, and then swim in the very cold water. But these emperor penguins find themselves in a pack called a waddle, and there they are all crammed together until one of them, under a lot of pressure from who knows what, falls off the edge. And they're all watching, hey Bob, are you okay? And Bob swims safely away. So now the second one bravely dives in. And then the next thing we know, penguin after penguin after penguin after penguin. These penguins, working from instinct, working from social pressure, are all finding their way off this death-defying leap. This is how systems change. This is how ideas work their way through our culture. There are different people who are choosing a different posture over a different period of time, all in reflection of the culture we have chosen to absorb. We are nodes, we have a limited amount of freedom, and it's culture that we are constantly dancing with. Thanks.
Okay, so my little penguins, we have 3 speakers. All the signs point to the rest of you hopping on the displacement ventilation bandwagon and making the leap into the cold ocean. But we're going to turn this presentation over to Mike and Kirk and Stacy for their experiences with displacement ventilation. Who's first? Kirk's. I am. All right. How about a nice hand for Kirk being our
Thanks, Tom. Why don't you go? There are the three of us. We've all been doing this quite a while. Tom asked us to kind of talk about our experiences, and this is meant to be more interactive. So if you've got questions, comments, please feel free to share them. My first experience was with displacement ventilation was back in 2010. We had a casino project that wanted to do a study, and at the end of the day, they had a couple of things that they wanted us to take a look at. It was, they had displacement in one area of the facility already and had decent success with it. And they wanted to understand, all right, what would be the impact if they applied that to the rest of the facility? So we were the first one in that aspect. Now, the reasons why they considered it because, like I said, their previous experience. They also wanted to reduce the amount of smoke for their guests and also for the health and safety of their own employees. Energy savings was on the radar, but quite honestly, it was really a low priority in the grand scheme of things. Some of the problems that we encountered, why don't you go to the next slide? Oh, I've got it. Was with Trace 700. It was kind of funny because Trace at the time, now keep in mind this is 2010, was saying, yep, we can do displacement ventilation calcs, but honestly, we spent hours and hours going back and forth with them in order to try to get it to make some sense. And eventually we were able to get there, but it was not an easy effort back then.
Well, you said at one point, you got to the person who had made the calculations.
Yeah.
And what did they say? I don't remember what they said.
I'm drawing a blank right now.
They guessed.
That's right.
So that 87% and that, what is it, 71% and 82% reductions for the occupants, equipment, lighting, and exterior, they put it at 50. So our math wasn't coming out great. So we were sending more heat to the plenum, but we weren't getting the full credit for it. But you know, you put the information into Trace, you get an answer, you don't know where the answer came from. So Kirk had to go all the way up to the guy at the top going, I guessed.
And it took quite a while to get there. Yeah. Then one of the next challenges that we had with it as well was how do we deal with dehumidification control? So we got a space with a ton of people in it. How are we going to deal with that? After we got past the calculation software, then we also had the concern, all right, we know displacement doesn't heat. How are we going to address that? Now, thankfully in our case, we had a casino which had a ton of heat loads all over the place. So that wasn't a problem at all. With that though, we had only overhead air distribution, and without major renovation to the facility, there was no way that we were going to be able to actually get airflow down to the floor. Our ceiling heights were between 12 and 18 feet, and our structure on that floor was about 32 feet. We all had a plenum return, so it was set up for success that way, but everything at that point talking about displacement was, all right, you got to bring it down to the floor. So we actually took the owner up to price and we did tests, and I've got the video. I found these videos that we did back in 2010, 2011, and they've got 3 or 4 different views to show you what's actually happening with the airflow. It was kind of interesting because at the time we did this test, they weren't sure either how exactly it was going to work. So it was kind of a test for everybody. And you saw the cardboard boxes. That was our estimation for slot machines at that point because there was nothing fancy and no metal enclosure that they had. One of the things that we found when we used the standard displacement diffuser was that the air distributed too much from the sides. And since we had a cloud ceiling, the concern was, all right, that in that space between the clouds, that's where all the return air went up. So how is it gonna work if we end up with air going everywhere where it's not supposed to, and we don't have an interface where the return air can actually make it back up through that? So I don't remember who exactly came up with the idea, but while we were there watching it, we had the idea of, all right, why don't we just throw a couple baffles on the sides and see what that does to the air pattern? And honestly, that's what we ended up purchasing at the end of the day. Found out that it worked amazingly well for our application, didn't throw the air too far. Tom talked about the 40 feet per minute. On these applications, on the high end of the airflow, we're at about the 50 feet per minute mark, but then it's still VAV, so it goes way down from there. And you can kind of start to see it. While you were there, it was a little bit more impressive because you could actually see it going through the slot machines and then distributing out. We also took turns standing underneath it to understand, all right, what does it feel like if you're underneath 52-degree air and it's all falling on top of you? We all were concerned that it was going to be an incredibly uncomfortable experience, and honestly, it really wasn't. We felt a little cooling effect, but it wasn't as drastic as what any of us had really expected.
So the plan was to just drop the air over or what, it's marked for where people are supposed to walk. So we found the clouds, found spots over natural pathways, so you're not sitting right under it while you're playing a game. But you know what? You could sit under it while you're playing a game.
And that's just it too. At the beginning, that's exactly how we laid it out. But what we found out later on was that they changed those slot machine layouts all the time. So what's an aisle today is going to be a machine in the future. And at first we were concerned, but after it was all said and done, there were no complaints. You also had mentioned about thermostat placements. So we did have thermostats down on the floor that we were monitoring temperatures with, but by and large, we had large single zone rooftop units. And we, more importantly, watched the return air temperature. Now, the interesting thing was that the owner didn't reap the full benefits that were available to them. They didn't want to turn the airflow down as far as what the study had proved out at the end of the day. Here are the various systems that we were talking about. At the beginning, they were 4 CFM a square foot, and it was constant volume and 100% outside air. So we did the displacement calcs, found out we can drop it more than 50%. However, the payback on that ended up being over 5 years. So as we were doing the study, said, nope, that's not gonna fly. So let's take a closer look at that and see what we may be able to come up with. That's how we came up with the hybrid system, which we used the 52-degree air rather than the 62 to 65-degree air. We're able to drop the airflow down even a little bit further, and got focus on energy involved in this. And as a result of that, we were able to we reached the maximum refund that they allow for a single location in a 1-year period, which up until this project, I'd never heard of anybody ever running into that. This is what it actually looked like at the end of the day, what our displacement diffusers above the ceiling. I gotta give the contractor a lot of credit because as we talked with them, they had the idea of going ahead and actually putting duct wrap on the outside of the diffusers. We've got cold diffusers, so we were worried about condensation. So we had an insulation system called out, but they suggested duct wrap. And quite honestly, that was an awesome idea because from the floor, even with the flashlight, you really couldn't see where those diffusers were. If you happen to catch one of the edges that you see on the flaps right here, you'd be lucky, but by and large, you really didn't notice it at all. Some of the problems that we had on this, So we had the 12 to 16 or 18 foot ceiling areas. Unfortunately, there were there was one area that had a lower structure than everything else. So we applied displacement there just like everywhere else. But as a result of that, it was a little bit stagnant there because there wasn't enough space for the returner to make its way back up to the large plen return areas. So we did that in phase one. After they had a renovation, then it became a no-brainer for them where, all right, we're just gonna apply displacement ventilation and it's the right decision for it. Here, while it was still under construction, you can kind of make out what the diffusers actually look like. In this area, we had 2 foot by 6 foot long diffusers, which wasn't a standard size that Price made at the time at least, and didn't have any issues. The return air basically comes up through the middle of this light fixture, and it worked incredibly well. At the end of the day, the aha moment for us was that the load's the load. The load never really changes. All that changes is where you deal with that load. So instead of dealing with the load in the space with your mixing system, the displacement system really just takes all of that, brings it back to the air handling unit level, and you deal with that load at the coil. So in this application, we had existing coils. We didn't have to replace them. We were fortunate in that they were 100% outside air coils, so there was never going to be a capacity concern there. But that's just one of those things that you gotta keep an eye out for.
Hey, Kirk, sorry to interrupt. Could you back up to the slide where you had the 3 different scenarios on the numbers?
Oh.
I just want to, so if I understood this, the far right column is the hybrid, that's where displacement ventilation, but a 52-degree supplier versus the center column was displacement with 62?
Yes.
So I'm trying to understand, I guess I would have assumed that the 62-degree discharge would give you cooling energy saving benefits. But I noticed that you only have slightly less total airflow with your hybrid. So in the lower discharge temperature, but so I'm just curious, the savings seem, okay, sorry, I'm looking at the wrong way. So that does explain probably.
And there are a couple things that are happening here as well that I didn't really go into detail. If you look at air handling unit 3 as an example, that was a 40,000 CFM area that it served. Full displacement, should have been able to get it down to 9,600, but because of construction and everything else, we honestly couldn't do a single thing with it. So it stayed overhead. Our only change was we made it VAV instead of what it was. So that's why it doesn't reduce the airflow, and that has an outside influence on everything else. Similarly for air handling unit 4, we couldn't do anything more than just getting it down to what the displacement values were. There was a minimum that we were trying to shoot for as well, because at the time, and seeing as this was the first one we did, we had a safety factor on top of it, just to make sure that if we had a problem, we had enough airflow that we could get it out there, and we had enough diffuser area where we weren't gonna have any problems.
Yeah, seeing this again helps me understand I was missing something the first time you showed it. Thank you.
So your loads were pretty constant all the time. You're using DX for cooling or
Chilled water for cooling on this chilled water.
Okay, and you're 100% outside air.
Mm-hmm.
So when it's 52 degrees outside and humid, what do you do?
So when it's at that point, we just send the 52-degree air out. Yeah. And we hadn't run into a problem with the humidity side of things because there's such a high sensible load in the overall space.
Yeah, and in a 52, you shouldn't. I mean,
Right.
even if you're doing cooling, you're coming off saturated anyway, off your coil. So it's no different than if it's 100% relative outside, 52.
Yeah.
What was the ROI on that with the therms and your KWs?
The ROI and thanks for asking. I did have a note about it. I just forgot to mention it. The ROI was a little under 3.5 years.
And the most expensive part, I assume, was reconfiguring the air handlers to reduce the airflow?
The air handling units, honestly, that wasn't where the real cost and where the real savings were. We did air handling unit upgrades where we changed filtration out on that. So I don't want to apply that to the savings on this or penalize the savings associated with displacement with that. The real cost on this was just going into the space and the disruption to replace all the diffusers.
And also keep in mind, this owner, when we first did, the first retrofit was just changing out diffusers. And I'm like, hey, you can cut the airflow down. And it was like, I don't care. Like, it's good. Like, yeah, but you're wasting a lot of energy. He's like, I don't care. It's good. Air quality's better. People don't smell the smoke. It did have a terrible problem with housekeeping because all the smoke that was suspended in the space dropped out. So all the tops of the ducts were covered in particulate. The tops of the gaming machines needed to be cleaned regularly because all this smoke and all the particles were suspended for such a long time, and then it dropped out.
The thing that really surprised me, so there was carpeting everywhere, and I was assuming that, all right, with all this smoke smell for this long a period of time, you're never gonna get the smell out. And I wanna say that 3 weeks after it was done, you could hardly smell any smoke odor at all. And my nose is really sensitive to that. So the fact that I wasn't able to smell anything really surprised me.
Kirk, it looks like, the diffusers usually are narrower and tall. It looks like that's how you install them. Could you have installed them sideways or something?
We did install a number of them sideways in that lower ceiling area. I think these were 4 foot by 5 foot diffusers. In the lower ceiling areas, we made them 3 foot wide, 2 feet tall. And I think we had 5 foot wide and 3 feet tall as well in that area.
So you don't need to have.
No,
There was a momentum benefit from a taller diffuser. So, as we drop the temperature, air's gonna want to get to the ground faster for sure. But there was also, dropping it from 17 feet, we did want to have having a taller diffuser with those sides on it created sort of it just did push it further. When we did other experiments, after it would pour off the side of the cloud, it would kind of peel off, like you're losing your outside layers because it's picking up heat. When we tightened it up and made it tall, it had no limit. We just wanted to get it through.
that is a good point too. That's the reason why we put the baffles on, so that we weren't afraid that we were gonna lose all of our cooling just back to the return air system. On another project that we had, well, that picture in the upper left really didn't turn out. We've got a hospital entrance lobby, and this was a really big, wide open space that on the lowest part of the ceiling, it was 32 feet. On the tallest part of the ceiling, it was 65 feet. All glass, all facing west, southwest. When we ran the loads using standard air handling unit or standard equipment rather, we had 40,000 CFM that was going to be needed for this space that was 5,000 square feet maybe. So it was ridiculous. So then after thinking about that further, we decided, all right, let's run a simulation, find out what it would be if we would end up with a displacement system. At the end of the day, we turned up that it needed 21,000 CFM instead. Earlier, I had a question asking how architects responded to it. So after we explained, so generally you would think that you're going to run into resistance. and that they'd want diffusers all up in that ceiling area. The problem is that they had big 4 foot by 4 foot tiles or larger, and then nobody wanted to cut into those. And after we explained the situation that we were in and the amount of space that we would need in order to get standard air diffusers in there, they were on our side at that point, and all right, let's work together to come up with a solution. At the end of the day, the solution turned out looking like this. What we were able to do is that we had diffusers that basically run right along here. Unless you were, while you're standing in the space, you'd have to look really hard to actually understand that those are diffusers that just look like a metal panel to the untrained eye. Some of the challenges with this space was that since it's an entrance lobby and we've got people coming from the outside, how are we going to keep this space warm? Since displacement won't heat, and there is no way that anybody was ever going to allow us to put destratification fans here. So what we ended up doing for that is that we've got perimeter baseboard at 3 elevations on that west and southwest face to take up or to deal with that heat load. Heat load rather. We did also have some other unique challenges in that if you follow those stairs up, they had an intermediate level that was like at the 1.5 story part where it was kind of a seating area because they had a cafe that was right underneath the stairs, or grab and go that was right underneath the stairs. So we were kind of struggling with how are we going to end up dealing with that. What we ended up doing there is we just put displacement diffusers just directly over the top of it for the load that we had there, and honestly didn't have a single problem. This unit uniquely, it's your standard VAV air handling unit. It's got chilled water cooling coil on it. It serves a space that's got displacement airflow, but it also serves spaces that don't. And as long as you know it from the start, you can make accommodations for it. How we dealt with the return air is right along the glass where our highest heat gain was really going to be all along. We put return air diffusers right up there, and you can kind of see it in the upper right corner here is one of them, but once again, unless you've got the right angle, nobody's really going to notice it.
Yeah, that was a neat one. Price did a really nice job. So that's a curved wall. It's not segmented. It's fully curved. So they built, I don't know if it was straight plenums or curved plenums, but it went together pretty nicely.
It did.
Yeah, and it looks good. Yeah,
And it's really comfortable.
Seam, yes. What was that?
It's really comfortable and you don't hear a single thing.
So what do you normally do for an atrium like this? Usually you're putting these wide slots on one side and throwing all the way across and trying to hit that glass and keep the condensation off of it. By putting the perimeter heat at 3 levels, they kept the glass dry, and then they just had to do a cooling load.
Kirk, was this a hybrid as well, using the 52, or is this using?
We did use the 52 to 55 on this one, but yeah, it was colder air. What we found at the end of the day was that there was really no downside from an engineering perspective and a practicality perspective. Nobody was complaining with 55-degree air.
Balancing conflicts or challenges with it?
Honestly, no. What we did, you can kind of see in the plan, every three displacement diffusers, we had a bigger plenum that kind of served all of those. And then we had round ducts running out to those, that each one of those could be balanced, so that you could equalize it along the entire curve.
And there's enough pressure drop in those diffusers that they're sort of self-balancing too. Get rid of a bunch of VAV boxes.
What's that?
You get rid of a bunch of VAV boxes.
We did. I forgot about that too. So that was another challenge on this. We didn't have the space to put any VAV boxes, so we ended up with one large motor operated damper with a small heating coil on it to just basically make it room neutral air And then you can see the two branches going to the left and to the right. Any other questions? Then I'll turn it over to Steve.
Thanks, Kurt.
So my first experience with displacement was corporate headquarters, central Wisconsin. The reason we went with displacement on this, it was really driven by the architect. They had these in the open office areas, they wanted high ceilings with a wood look that was tucked up between the beams. And so they kind of drove that it was going to be an underfloor system. So we, the issue there was the owner had an existing underfloor system that they were not happy with because it was a mixing system. Everyone was uncomfortable with the air blowing up. I could hold my hand this high above the floor and feel the air coming up. And so they wanted to make sure that that didn't happen again. And so talked with Tom a little bit about using displacement and underfloor, and then got some videos from Price showing the difference between the two, so I could convince the owner that with the displacement system, they weren't going to have the same issues that they had in their existing facility. So this building was 3 floors. The upper 2 floors were all open office space, and that's where we did the underfloor system. You can see in the plan view, we used fabric duct in the underfloor plenum to distribute the air, and then we had diffusers throughout. So that picture shows the fabric duct in the underfloor, which kind of, as a sidebar, became an issue with the inspector.
Oh.
I think it was Tom's suggestion to do it, but
Damn it.
the code states that fabric duct is to be installed in the area it's serving, exposed in the area it's serving. So we ended up having to get a variance. We convinced them that the underfloor plenum was the area it's serving.
Was the underfloor a pressurized plenum?
Yeah.
Okay, thank you.
So this is the open office area. We had panel radiators at the perimeter for heating. And then every cubicle got their diffuser, and then along the windows, we had a whole line of them.
So just Stacy's talking briefly about, there's 2 different kinds of floor diffusers. There's one that's more traditional open office, where it's called a twist, and it actually brings the air all the way up here, and it's designed to. It's a full mixing device. So the benefit of, so what's nice about those is you can get more air out, right? They're more turbulent. There's more, you can get more air out of each one. So theoretically, you can have fewer diffusers, right? So there's the benefit for the installed cost. The negative side is because it's so turbulent, you're doing a mixed air calculation. So you've got the underfloor, you've got all the elements of a displacement system, but then you kind of throw it away by using a diffuser that's got more air. So when Stacy changed it to a displacement diffuser, yeah, we had to put more pucks in, but she was able to reduce, I assume we were able to reduce the airflow in those systems, yeah.
Yeah, the airflow in the open office areas was about 0.55 CFM a square foot.
Right.
So. Then part of the 3rd floor was an executive suite, so it had enclosed offices. Here we just put some of the fabric duct into a central area, and then we use underfloor fan power boxes. No reheat in those, just the fan pushing the air into each office area. And then the building was in 2 wings with a central lobby, 3-story lobby area. So in the lobbies, we ended up using displacement ventilation there too. with the diffusers on the walls. I think this band here is the diffusers, and that happens on both sides of the lobby. We have 3 levels of panel radiator at the windows. And those diffusers are about 10 feet off the floor. And then we have D-strap fans tucked up in between the wood slat ceiling. And then we also did a custom column wrap in 4 locations. Worked with Price on doing that custom. It's actually a 3-sided diffuser with the duct connection off the bottom because the mechanical room was right below it. And then in the end, they ended up putting the tabletop and stools right up next to it. And then there's the full lobby. So we've got the displacement diffuser there.
I don't know, Stacy, I think we should run ductwork across this thing. And look like that.
Yeah.
That's awesome. Nice job.
And then I just did another displacement job that's currently at the end of construction documents. It's a large lecture hall for Carroll University.
Stacy, just out of curiosity, did you ever sit in one of those chairs at that table around the diffuser? Just curious if it's comfortable with your legs that close to it, or is that more just, they made it look like some people, you could sit there, but people don't tend to use those?
I haven't heard any issues. I haven't heard of any issues with this project.
If you go up to a displacement wall diffuser that's this tall, to feel it, you have to be at the top of the diffuser, you have to be within an inch of the face. I mean, think about, it's coming out at 40 feet a minute, slowing down. Walk 40 feet in a minute. It's incredibly slow. It's just incredibly slow. So,
And to add on to what Tom's saying too, on the casino job, we had a high roller area where we were able to get displacement diffusers down lower, and we basically enclosed them in columns. I didn't think to include any of those pictures, but they were 7 feet tall and 3.5 feet wide. And like Tom said, until you're actually hand right up against it, basically, you don't feel it. And there were chairs right next to it, chairs right next to it, and table games right next to it, and nobody even noticed it.
And then just add on to Stacy's, for those who didn't make the last ASHRAE tour, they toured headquarters.
Right.
And what?
Right.
Headquarters. And they also did underfloor with fabric ductwork. I know their competitors, but that's how they designed it too. I don't know if they needed a variance, but I noticed that they promote pitch using fabric ductwork underneath the floors to get the cooling where you need it.
All right, Stacy, thanks.
So my first experience with displacement ventilation was about 10 years ago.
You gotta introduce yourself.
Oh, hi, I'm Mike Bartley from DuChateau. So like I said, my first experience was about 10 years ago. It was at the University School of Milwaukee.
That's not true.
Yeah, I think it is.
Experience was at the Basilica.
No, that was Dennis. That was
I thought
Dennis.
you were assisting Dennis.
I was not,
Oh, I think it's that.
So, and basically, why I went with it was purely aesthetics because of the fact that the early renderings of the space, let me see if I can, showed all this natural, these wooden beams, and just the thought of putting spiral ductwork through there was just, it was just not an option. Talking to the architect, they were like, yeah, that if you cannot put spiral duct through this, that would be wonderful. So what we did is I talked to Tom, and he introduced me to Price Room Designer and did all the calculations and utilized the Price, I think it's DLE-H, which is the displacement cabinet with the top that's all fin pipe radiation in the top there. So that worked out really well. The return is up high in the space. This is served by a single zone air handling unit, DX, with the hot water coil in the reheat position. So basically, we're discharging, dehumidifying, getting that temperature and that moisture out of the air, reheating it from 55 to 64, and discharging it into the space. But we also have another sequence that, it's kind of a pre-event, or, before the kids get their morning warm-up, as Tom explained before, that what we can do is we can reset that discharge air temperature off the heating coil. I sized the coil for like 80, maybe 85 degrees, even though we do have perimeter radiation, just another, I guess, tool that you can use to warm up the air. And then when we do reset that temperature, we do have destrat fans hanging in there, but I don't know if you can necessarily see them at all. You can't really see them, but they are in there. So yeah, so we just did the whole perimeter. The contractor did, I think, a really good job matching the wood. Price did an amazing job, with the sizes. We weren't able to use exact catalog sizes because the length wasn't exactly perfect, 36, 24, 48, or whatever they come in. So they did a fantastic job, and it's just, I think it's, as I was talking to Tom, one of the crown jewels of the campus, I think. Yeah, so basically, there is the displacement diffuser on each side, and that ductwork is just going up into each of the cabinets from below. We do have energy recovery on this system. The only thing that I've noticed with displacement and energy recovery is that in the cooling season, it can be very difficult because your return air temperature is so high. So if you have a, 89 degree return air temperature and your outside air is 90, there's really or not much savings there. But yeah, the space is great. Never felt any drafts. Like I said before, the room designer, you can look at temperature, you can look at draft ratios. Layout, you can move your diffusers around, and that's basically what I did. Is I built that box in Room Designer, and I placed all my diffusers along it, ran the calculations, ran the draft ratios to see where we were at, and went with it. Now, a big thing with this type of system, though, is that there was a basement plan for this already, so I didn't have to fight too hard. So, that makes life so much easier. All we really needed to do was get that return ductwork up high. So it's one shaft versus, trying to get a supply shaft up there, and then distribution. It's a clean system, and the school loved it. Yeah.
And you've done other projects such as?
Yes, so I have done Madison Youth's Art Center Theater with a pressurized underfloor plenum. I've done Incapsis Lobby that has kind of like Stacy's with a really big displacement diffuser. We also did displacement in their lounge, but we had to be very careful because there's a radiant floor there, which completely can mess up your airflows and temperatures. And currently doing the Milwaukee Rep Theater, which is not a pressurized plenum, it's individually ducted floor module diffusers. And the goal there is for Tom's mom to go and watch a show and not be cold. That's all I was saying.
True story. And you did Christ Church.
And Christ Church, yeah, that was an interesting one. That was rooftop units, but huge gathering space. And for that one, we had, to get the temperature and dehumidification down, we did a DOAS unit coupled with a rooftop unit. So that was kind of an interesting situation, but same thing, destrat fans. We hid the diffusers in kind of like I don't know how to describe it, encased them in like woodwork or whatever you want to call it, but it's basically it.
What am I saying for Mike? Thank you guys all for coming, and just remember your takeaway is number one, if you ever see anything Stranger Things, you're gonna think of displacement ventilation, airflow, and price. And number two is I hope you guys see the benefits of applying displacement ventilation more than just like, maybe once in a blue moon. It fits in a lot of applications, and our three speakers who did a great job are showing that, You're just a bunch of penguins, you're just ready to follow these three leaders, so. All right, so thank you all for coming. If you're here live, lunch is served, and for those of you in our remote audience, thanks for coming, appreciate your time.
Thanks, Tom.
Thanks.
Thanks, everyone.
All right, let's grab some lunch.
That never happened.
That's remarkable. No, we finished it.